Okay, we're going to wrap up 5.3 by looking at the domain of the log function, and then I'll work one application example showing how all this stuff works in a real-world problem. Anyways, we already looked at the domain, but that's assuming the simple case here, and what we're looking at is this right here. Okay, so in the simplest case, when you just have x there, and we looked at graphs and all that, it goes from 0 to infinity. That's a requirement. But what if that's like a little function or something? Let's look at a couple of examples here. Let's start with this one. So now, that whole thing right there is x. That's the argument. That's the number we're looking for the log for. So if x has to be greater than 0 and can run on out to infinity, then all we need to do is look at this expression here and say, when is that expression greater than 0? Well, when what's inside here is greater than 0. The square root of anything greater than 0 is going to be a positive number. So that's all we need to do in this case. I want to know when that is greater than 0. Well, if I add 3x to both sides, then if I divide both sides by -3, so as long as x is less than or equal to this number, that's our domain. So our domain is, we can go all the way to negative infinity. X can be as small as we want, but when we get to -5/3, we have to stop. So that's actually the domain here. Let's look at one more where it gets a little more interesting. Okay, here we've got a couple of things going on. Okay, the first thing to notice is this: when we're looking for domains, it doesn't matter what the base is. It doesn't matter if it's base E, base 6, any base. That's beside the point. All we're looking at is this argument here that is replacing x. And we want it to be greater than 0. So if I look at this one, if the top is greater than 0, or we can just do this because we're not sure here what's going to happen. We'll see why in a minute. We're concerned what happens when x minus 2 equals 0. Because we have a denominator here, we're not sure what's going to happen on either side of 0. So 0 is a critical point. So if the top equals 0, we got a problem. Okay, so let's solve that. So that's pretty easy. So we're going to have to look at a number line here. If x equals 2, we can't be there, but we got to be on one side or the other. But in this one, we also have that situation where we have a denominator, and the denominator can't be 0 because that's undefined. So this was kind of like hunting for asymptotes, if you want to think of it like that. So I also have a problem here. I can't have x plus 3 equals 0. So that means that x equals -3, we have another problem. So kind of like we've seen before when we're looking at stuff, Okay, we can't equal 2 or minus 3, and those set up some regions. And what we're trying to do then is find out, when does this guy right here, when is he greater than 0 or positive? So again, choose a test point. 0 is sitting within this range. Let's just plug in 0. I'm not trying to evaluate, I'm just trying to figure out if it's positive or negative. So 0 minus 2, 0 plus 3. Well, that's going to be a negative over a positive. That's a negative. So that means this little guy right here, this expression, is negative in this range. It's going to be positive then here and here. So our domain then starts at negative infinity, goes to minus 3, and then we pick it up again at 2, and we run on out to infinity. So that's how we find the domain of kind of more complicated log functions. And we've already kind of done this earlier on, trying to find the domain of some other functions. So it's a similar task. All right, let's go to one application problem. And logs are used a lot for all kinds of problems, growth and decay problems. This one here, which happens to be measuring sound. So we look at the introduction up here. Sound intensity is measured in decibels. They're just referred to as dBs. I think we've all heard about dBs. Something real quiet like a whisper, that's going to be between 15 and 20 dBs. And then when you get into really loud sounds, like in the 120 to 130 range, those can actually damage your eardrum. So here's the equation that models it, and it includes a log function. And here's the definition of these things, but basically that's your actual measured sound intensity. I0 will be a constant, and it's kind of set up for the experiment. In this case, I0 is the faintest sound perceptible to the ear in this case. So even though it's I0, it's kind of a starting point, but it's called a reference intensity. So you can think of it as the smallest, the starting sound, the smallest sound in this case the ear can hear. So it could change for a different situation. Anyways, in our case, we're going to use 10 to the minus 16th for that faint intensity. And then, of course, this is just the decibels at that intensity. So dB measure for sound I. One other thing in this problem, and it won't show here, but on this second part, when you're trying to find out an answer for I is a multiple of I0, so you're going to wind up getting something like I equals something times I0, or in our case, our answer down here has got to look like I equals some value times 10 to the minus 16th. Okay, that's all this means. Okay, it's a multiple. All right, so let's look at the first one again. This is just using equations. Start with your basic equation, plug in what you know, and just solve for the unknown. We're trying to find the dB, so we're solving for dI. We don't know what I is. Find the dB, so we don't know what dB is. Here's the sound intensity here. So we know what the sound intensity is. That would be I, so that goes up here. And then I naught is basically a constant, so that's not going to change for our situation. Okay, so we want to take a look at this now, and we need to take care of this here. So if you take a look at this, this is just back to our old exponent rules, where if I want to get rid of this one down here, I subtract it, and be careful here. I subtract it from this value. So see what happens here? We're going to wind up with a plus. So it'd be minus 14 plus 16. That's going to be 10 squared. So di equals 10 log, and what is 10 squared? It's 100. Okay, so we can finish this one up by just going to your calculator. If you put in 100, hit the log key, it's going to spit out a 2. So you can get that right off your calculator. So what we're looking at here is an intensity of 10 to the minus 14th gives us 10 times 2, that's 20 dBs. Okay. So let's kind of work the equation the other way now. Now we need to find the intensity, but we know what the dBs are. So we have 83 dBs here. And fill in our equation. We're trying to find the intensity, so I is unknown. But we know what I0 is, 10 to the minus 16th. That's our constant. Okay. So we want to start isolating the log term. So I'm going to want to divide both sides by 10. So 8.3 equals, so we're dividing both sides by 10. Okay. Okay, now we can't evaluate this thing with the calculator and that, but what we can do here is let's go ahead and convert this from log form to exponent form and see what we can do there. So remembering that there's a base 10 here, I have the base to the power. Remember the exponents here, the numbers here. So base to the power here, or exponent, should equal this number. Okay, that's easy to solve for I. Just multiply both sides by 10 to the minus 16. And go back and remember this. We want to keep that 10 to the minus 16 because I equals a multiple of this. What I'm interested in is, what is this number right here? So 10 to the 8.3 times 10 to the minus 16 equals I. So that's technically the answer right there, but if you go to your calculator and you put in 8.3 and you put in the 10 to the x key, then you'll get this number here, which I believe the book showed as the answer. Now there's some decimal points, but we're rounding to the nearest unit. So either one of these is good. Basically, I is a multiple of I naught, or 10 to the minus 16. So these are your answers here. Again, either one. Okay, and that's it. And most of the application problems are similar. You'll be given a function with the logs in it, and you just work with them, sometimes directly, sometimes you convert to exponent form, but you may wind up having to use your calculator, either the log key, the ln key, or the 10 to the x key, or the e to the x key, depending on the problem.